Thank you. Thank you, everybody. Okay, first and foremost, can folks in the back of the room hear me? Okay. And how's the audio on the microphone? Okay, great. Excellent. Thank you all for having me here. Thank you for inviting me. It really is an honor to come speak. I literally grew up on this campus, so it's very heartwarming to be here and to be with all of you folks. I am going to insist that people ask me questions during this, and if people don't ask me questions, I'm going to call you out, so be prepared, okay? So I think you guys all know I grew up in Wolcott, Vermont, and it makes a great story. A one-bedroom log cabin with an outhouse. Okay. We did have running water, we had a real bathroom, but that was where I grew up, out in nature, enjoying it, you know. Oh, North Wolcott, all right, that's where I grew up. It was North Wolcott.
I lived there for 30 years.
Nice, and I am glad you're here. Thank you for coming. That's fantastic. I have someone from my hometown. Okay, so super quick overview. I'll tell you very briefly who I am and what my job is, and then I'm going to talk to you folks about space weather and how science funding works. So this is really important because if you think you want to be a scientist, you're going to have to compete for money, and my job essentially is to give money to worthy grant proposals. So we'll talk all about that. I'm sorry, there was a question?
You're like Science Oprah.
Science Oprah? Is that what you said? Oh my God, I love it. That's great. I never thought of that. I love it. Okay, so this is a little bit about my career. I'm going to get this movie started. I went to Stowe High School. I was not particularly interested in math and science, although I did really love biology, and I took physics in high school, and I thought, well, this is kind of okay. But after high school, I really didn't know what I wanted to do. And I said, rather than spending a whole bunch of money on an education, and I'm not sure where it's going, I'm going to take time off. And this terrified my parents, absolutely terrified them, right? It looks like I have no direction. Oh my God, what's happening to their child? But that turned out to be a really important time for me. That was where I figured out that I really did want to have a career, that waiting tables was not going to sustain me for the rest of my life. And I started reading some popular science books on particle physics, and I thought, this is really fantastic stuff. I think I'll check that out. I don't know if it's going to work out, but could it really go wrong? If you start studying science, you're going to end up somewhere. So I went to University of Vermont. I spent 4 years waiting tables, and then I went to the University of Vermont and got a bachelor's in science in physics. And from there, I went to the University of New Hampshire, where I worked on a Ph.D. in plasma physics. Now, this is not what I thought I would study. I had no idea what plasma physics was until my senior year of college. But that's where the job opportunities were. And my favorite math professor in college was teaching a plasma physics course. And he called me and said, I want you to take this class. And I was honored. I mean, how amazing would it be if a professor called you and said, I want you for this? So I took his plasma physics class, and then I went looking for schools and opportunities where I could study plasma physics. And that was how I met my thesis advisor. So I ended up working on something that was borderline related to fusion, which I thought was amazing. And I thought, this is what I want to do. I want to do fusion. But that's not what happened to me. The sun happened to me. So I was working with a group that had collaborators at NASA Goddard Space Flight Center, which is in Maryland. And that's me with some of my pals. We were postdocs together down there. And I started watching movies like this. And I thought, I have no idea what's going on here, but that is so cool. I have to figure out what's happening. So that's what I did. I spent 5 years working on the fundamental physics of magnetic reconnection, which is something we will just talk very, very briefly about. But it's basically how big eruptions get started on the sun and how they propagate through the interplanetary medium and what happens when they hit Earth. So it turns out that this phenomena happens not just in space, but it happened in fusion devices too. So I thought that was really cool. Now, I did something called science advocacy. I don't know if you folks know very much about that, but I went down to Capitol Hill and I spent time in Bernie Sanders' office and Pat Leahy's office talking about how important this science of space weather and the sun is to Vermont and to the entire nation. And that got me connected with folks that at funding agencies like the National Science Foundation and at NASA headquarters. So a job opened up, and I applied for it, and they gave me this opportunity to go manage grants programs. So I don't do science anymore, but what I do is read proposals of all of the scientists that work in this field and run competitions to determine whose science is going to get funded. So in the last year, I started managing facilities. So I manage radars. This one here on the bottom, it's a radar that's in Massachusetts. That's at MIT's Haystack Observatory. So that measures the upper atmosphere, which we'll talk about. And then the other one here, sort of in the middle, is Arecibo Observatory in Puerto Rico. How many folks know what Arecibo Observatory is? I see a couple of hands, just a few. Arecibo was in GoldenEye. It's been in a couple of movies. Big giant dish that's in the ground. Coolest thing ever, and I am so lucky to get to do this. Okay, so let's get down to some science. This is the Aurora Borealis. So you guys all know this, right? You know the Northern Lights. No, I'm seeing shaking of heads. How many folks have seen the Northern Lights here? Okay, awesome. If in the winter you get a chance, you hear that the auroras are happening, go outside and look. It is amazing. There are scientists that study the auroras for decades and have never seen it. So you folks are in a really unique situation where you can just go outside and look up and see this incredible phenomena. So this is happening. This was taken on the International Space Station. The auroras essentially happen all the time, but you can really only see them at night. And you can see all sorts of fascinating phenomena happening in here. Let's see, there was a pointer, right? There's some stuff that looks like it's kind of pulsing, and there are these streaks that are happening in here. And scientists don't really understand why this happens. I mean, we sort of know why, but not really. All right. So let's start from the ground up. Now you know, auroras are like, we want to figure out what's happening with auroras, okay? The radars that I manage study the upper atmosphere, like way up here, okay? So it's way above the atmosphere that we can breathe. So up above the atmosphere that we can breathe, that we live in, the atmosphere becomes charged. So we have positive and negative charges floating around. It's called the ionosphere. And the positive and negative charges floating around together are called a plasma. It's the fourth state of matter. Have folks heard about the fourth state of matter? A few? A little bit, maybe in high school, you know, maybe? Okay. So all of this research that we're doing is on plasmas. It's all happening in the upper atmosphere. And then beyond the upper atmosphere is all of these crazy dynamics. There are these things called radiation belts where you've got particles flowing along the magnetic field of the Earth, back and forth, bouncing back and forth. There are currents that form. It's incredibly dynamic. It's weather almost like the weather that we experience, but electrically charged. Okay, so if we go further out from the ionosphere, way far out, we have Earth's magnetic field. These things are called radiation belts. There's a lot of particles that are trapped in there. They bounce back and forth. This radiation environment is where our communication satellites sit. And so scientists are trying to understand the dynamics of this system and their impacts on communication satellites. There was something called the Van Allen probes that went up 4 years ago, I think. And they discovered a third belt. Like up until that point, we thought there were only two, and then it turns out there's a third one. And the scientists just went totally crazy. Oh my God, what's happening here? This is so cool. So these are the radiation belts. And then this is the boundary of our magnetic field. So Earth's magnetic field is generated by the iron core that we have, the iron molten core that's spinning. It creates this magnetic field, and this magnetic field is our protection. It's our force field. It protects us from the radiation that comes from the sun. It's incredibly, incredibly important to life on Earth. And so when scientists are out, like planetary scientists are out looking for places that are habitable for us in other solar systems, one of the first things they look at is, what is the structure of the magnetic field? Is there a magnetic field, and what is the structure? Is it strong enough to protect life from whatever the star might throw at it? All right, so if we back out a little bit further, you can sort of see the structure of this magnetic field. It kind of looks like a spider, and I just thought that was so cool. So here's this is called the bow shock. This is the boundary here between the sun's magnetic field and our magnetic field. And this is the day side. So, there's one side of the Earth that's always pointing towards the sun, and that's day, right? And then the other side is night. And in the night side, the magnetic field is stretched out, and all sorts of turbulent dynamics happen. So it's like a rock in a stream. There's one side where it's sort of rounded, and then the back side, it's kind of long and turbulent. And that's exactly what's happening here, but it's happening in a plasma state. Okay. So then the next slide, I'm going to show you a graphic from NASA of what space weather is. So the basic idea behind space weather is that the sun is always spitting out material. You saw how dynamic the sun was, right? That was a picture from a very active point in the sun's cycle, okay? So the sun's always spitting stuff out. It's coming towards us. They say, space is a vacuum and nothing's happening out there. Baloney. It's total baloney. There is tons of stuff happening out there. And that's what the study of space weather is. So we're going to see a big giant blob come up off of the sun and propagate to Earth, and then you're going to see the impact at Earth. And you're going to see magnetic fields sort of peel off the Earth like an onion and come back into the night side here, and it's going to smush together, and it's going to bounce in towards Earth, and you're going to see particles propagate along the magnetic field lines down to the poles, and that's how the auroras happen. All right? I thought this was the coolest thing. Yes, Caitlin.
What kind of material does the sun spit out?
The sun spits out plasma. That's an excellent question. It's mostly hydrogen and electrons. Mostly. All right, so here we go. We're going to see a big blob come off of the sun. And that big blob is called a coronal mass ejection, which is just a terrible name, but that's what it is. Yes, it is massive. It is absolutely massive. Here's Earth and our beautiful magnetic field, and it's peeling sort of back around. And back here, we're going to see there's going to be a bright spot, and that's magnetic reconnection. So that's magnetic field lines kind of smushing together. And there's the particles. They bounce along the field, and they come down to the auroras. Okay, this is a lot of material, and this took me years to understand. So does anybody have questions about any of this? Somebody has a question.
Remember, identify yourself.
Yes, yes. What's your name? Yes.
Hi, I'm Deb. My question was, so it's not harmful when plasma hits us?
Excellent question. That is an excellent question. If the plasma hits us, it is harmful. So when the astronauts are in the space station, one of the things we need to protect them from is this radiation. And one of the wonderful things about our planet is that the magnetic field protects us, and other layers of the atmosphere protect us on the ground. So if something were to happen, which is like the Carrington event, it was this great big event that happened in 1859, where the magnetic field of the Earth gets pushed, like say some super disastrous thing happened and the magnetic field of the Earth got pushed way into inside the planet, We would be completely exposed to the solar radiation, and that would be a problem for humans. Yeah, yeah.
So, is this a totally different situation, but will climate change affect the magnetic?
That's a very good question. Would climate change affect the magnetic field? And fortunately for us, it doesn't look like it. Yeah, we're kind of lucky. So the field, the layer of the planet that we live in that's affected by climate change is very far separated from the magnetic field. So to be perfectly honest, I'm not sure that scientists know if there is anything that would affect the magnetic field of the planet, except that the magnetic field has its own cycles to it. So there was a question right here.
Yeah, just like the ozone layer is supposed to be ozone layer. So that is totally
Good question. Holes in the ozone layer.
sorry, I'm a from the current topics class.
I'm sorry?
I'm from the current topics.
Oh, okay, great. Excellent. So the ozone layer is very, very far down compared to all of this. So what scientists say is that these systems are decoupled, which is a nice way of saying we don't think they really interact or affect each other. Although there are effects from down below that go up too. But it's something different. They're called gravity waves. So anyway, we can talk more about that. Yeah. There are effects from down below and up, but they're not related necessarily to climate change. They're more related to winds that happen high up in the atmosphere. Those winds can push on the plasma of the ionosphere, and that can affect changes that can impact the magnetic field further out. Oh, excellent. So many questions. You had one.
I'm Sarah. I'm in the current topics class. How did scientists go about deciding where to put the satellites? What does the aurora borealis, how does that impact the satellites? And why did they put the satellites where they do?
Okay, that's a really good question, and I don't necessarily have an answer for it. But what I can sort of generally tell you is that the scientists say, we want to look at this thing, let's put a probe there. So that's kind of what they do.
How do they do that with your money?
Yeah, with taxpayer dollars, yes.
Is there enough of a magnetic field around those satellites to actually protect them from?
No, that's a good question. If you are inside Earth's magnetic field, then yes, but there are probes that are outside, like Voyager and a few others. Those are not protected by a magnetic field, so they have to be radiation hardened. Yeah. There was another question. Yes?
Melissa, so my question is, when the plasma comes back to create Polaria, what necessarily determines the colors or the location of
Excellent. So the question is, what determines the colors and the location of the aurora? Okay. So let's see. Can we see from here? I'm wondering if I have a good graphic for this. Let's go back here. This is not ideal, but it'll work. So the magnetic field of the Earth does this, right? You can sort of see it here a little bit. It kind of does this. So it's very strong at the poles. You have very, very strong magnetic field there, and sort of weak magnetic field here. So there's something called the auroral oval, which is where most of the particles precipitate. So they come along the field and down onto the planet, essentially. I don't know why the auroral oval exists exactly where it does. I just know that it is there. The color is determined by what species, what elements in the atmosphere are being charged. So what happens is that you have these particles, they're mostly electrons, they're propagating along the magnetic field, and they come down and they hit the atmosphere, right? And the atmosphere is sort of neutral. And so when you put energy into some element, to some atom, what happens? Somebody in chemistry must know. Yes, Caitlin.
That's how they do the fire test. I was going to ask you kind of connect the colors to the aurora, to the fireworks.
To fireworks. Okay, well, let's come back to this one.
Mostly with
Almost. Yes, yes. Do you have the answer?
Like the electrons start moving, and that's when you start seeing reactions.
Exactly. The electrons in the atom start moving. And if you put enough energy into an atom, you can pop an electron off. And when you do this, when this reaction happens, energy is released. And that energy is light. And depending on what wavelength of light it is that's being emitted, you get a different color. So I can't remember, but it's mostly
Green. It's mostly green. I've never seen red before.
right. So I think green was nitrogen and red was oxygen, but I could be wrong about that.
Oxygen lower down is green, higher up forbidden emissions of red.
Okay, there we go. This guy knows.
Nitrogen is also red, different.
Nitrogen is also red at a different
Yeah.
altitude. Okay, excellent. Yes.
Rick McMahon, NASA Solar System Ambassador Volunteer. You're absolutely right about the magnetism helping our planet greatly. They're thinking now that Mars at one time had a stronger magnetic presence than it does now. And with that dissipating, that's what led to the atmosphere being basically blown away by the solar wind. So because we have the magnetic system of our planet, we are on a Goldilocks planet.
We really are. We really are. This is very special. The magnetic fields of the other planets are so cool, and if I had hours and hours, we could go into the different configurations and the angles. But when I started learning that different planets had different magnetic fields, my mind was totally blown. It was just the neatest thing. Okay. All right, so I'm going to show you very, very briefly. This is a simulation that was done at NASA Goddard Space Flight Center. We are looking down on the solar system here. So what we're going to see is what it looks like when a big eruption happens on the sun and it propagates through the solar system. So we have the sun in the middle right here. We have some satellites here, and let's see, there's Mars and there's Earth. And this spiral shape is basically what the sun's material looks like. So when it's spinning, and it's spitting off material, and so it spits out this spiral, and it also does this wavy thing up and down like this. So it's really cool. But we're looking down, and so you're only going to see the spiral. And you are going to see an event that happened in 2012. So this event was so big that if it had been directed at Earth, the scientists believe that very significant damage could have happened to our communications infrastructure, to our power grids. It's on the scale, they believe, of an event that happened in 1859 called the Carrington event, which was such a strong eruption that when it hit Earth, they saw auroras really far south, like Colorado south. And I'm sorry, Cuba? Havana. And there were reported stories of telegraph, like paper at telegraph offices, erupting into flames because such strong currents were flowing through the telegraph wires. So people are generally concerned. Governments of the countries across the entire planet are generally concerned about what happens if something like that happens today, because we are so dependent on electricity.
Dark ages.
This is the fear. This is the fear. So yes, Caitlin.
Sorry, Caitlin. Sorry to bother you. I was wondering, did scientists just notice this happening, or did they predict that this was going to happen?
So the question is, was this predicted? Predictions, we like to say in our field that the ability to predict space weather is about 50 years behind the ability to predict terrestrial weather. So you can see features on the sun and know that their complexity is increasing and that maybe there's going to be an eruption, but the predictions are not very good right now. So a lot of the research that we fund at the National Science Foundation is what is the fundamental physics behind these things such that we can build predictive models that agencies like NOAA, the National Oceanographic and Atmospheric Administration, would use to predict and protect. Yes, what was your name?
Alex.
Alex.
And
I was wondering, like, obviously you're not sitting there staring at the sun with a telescope, but what's the imaging that you guys use for looking at the sun?
Excellent. So what is the imaging that we're using? There are telescopes that look at the sun, but the best way to track the sun is to use satellites. And so NASA has satellites that are orbiting around Earth, and there's also a satellite that's sitting at a special place that's called Lagrange Point 1. It basically sits in a safe, gravitational safe space between Earth and the sun, and it's always looking at the sun. And so there are scientists that sit and watch the computer screens, basically. It's a little more automated than that. They get warnings when something's happening, and then they rush and take a look at what's going on. And then they feed stuff into models like this. So you set me up perfectly. Thank you for that. They feed information into models like this that then are supposed to predict where is this thing going and what's the impact going to be. So this is what we're going to see. We are going to see a massive event that happened in 2012. This was the prediction. Oops, let's see if my movie's going to work. Here we go. So this was a multi-stage event. We had a big eruption here. That one actually hit Earth. And then there were some little blasts. And there's a big one. That thing was so fast that it went from the sun to the orbit of Earth in 18 hours. Incredibly fast. There's almost no time to do anything when you see that thing coming right now. Okay, now that sounds all very scary. It's not as bad as all of that. Okay. We have things that we can do, and in fact, there are power grid operators here. Where's VEC? Vermont Electric Co-op, they're right here. What, Johnson, Hyde Park? Johnson. They actually monitor fluctuations in their power grids, and they look for stuff like this. So I got to see the Rock Lab today. This is all connected, I promise. I got to see the Rock Lab today, which was the coolest thing ever. All right. One of the really fascinating things about this planet is that there are rocks in which currents can be conducted. And there are regions that have a lot of this. And so if you have a power line, a big power line over a region that conducts a lot of electricity, and you have this great big, power line, and there's currents flowing across it, and there's current flowing beneath, it just intensifies the entire situation. So the concern is that you have these intense currents flowing through the power grid, through the lines. They get to a substation and they hit a transformer, and the transformer can't handle the load, it explodes. Okay, so this happens somewhat regularly across the planet. Like I'm not sure how many times a year, not dire, but it does happen regularly. And so folks at northern latitudes, like Vermont Electric Co-op, monitor these things, and they look, was there a space weather event? We see a big fluctuation. Was that coming from something natural outside? Was it coming from inside the grid? Was it coming from somewhere else? So people in this area are all paying attention. They want to know what's happening here. Okay. So these currents that flow through the rock and they flow through our power lines, they also can flow through communication satellites. And so the big concern is that the entire network of communication satellites would go down if we're hit by a big thing like this, and then, good God, what do we do? So fortunately, satellite operators are also paying attention to this, and if they know that something's coming, they can put their satellite into safe mode, which helps quite a bit. Okay, anyway, I was at Goddard in 2012 when this thing happened. It was so exciting to, we think something's going to happen, and then boom, 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 there are these events, and then holy cow, this massive thing happened, and we were so lucky that it was directed out the backside towards Mars, and it hit this satellite that's called Stereo A, which was monitoring the sun, and basically fried it. So we don't have access to that anymore. Yes?
Is that an example of a solar shower? I've heard solar showers before, and that's a lot of electronics don't work properly.
Yes, but I think solar shower is a slightly different term than the one I'm familiar with. So, yes.
Same thing coming from the sun.
Yeah, it's the same thing coming from the sun. Exactly.
So Earth is where
Earth is this little blue dot right here. Let's see, and Mars was here, but our satellites were here. So the stereo mission was actually really cool. It was a NASA mission that was supposed to look at the sun in stereo, because right now we just have satellites essentially sitting right here, so you only get one view on what's happening on the sun. You can only sort of see it coming towards us, basically, and we want to know, what does it actually look like in 3D? So that was an attempt to do something of a 3D rendering, and then we lost one of the satellites. Okay. Parker Solar Probe is just recently launched.
Right.
Yeah.
It's going to do 24 orbits in 7 years.
Yeah, Parker Solar Probe is really, really interesting. So that's going to go way down. It already has gone really closer to the surface of the sun than any satellite has ever been. It's absolutely phenomenal. Okay, there was another hand I saw. Yes.
My next question, what was the timeline for all of these explosions happening?
Oh, I don't have the time on there. This happened over a matter of days. So it was like a week and a half, maybe, period. Yep. So the sun has these 11-year cycles where it's really, really active. The magnetic field of the sun is like Earth's magnetic field, right? It's this big dipole. It's like a bar magnet, more or less. And it gets super twisted up. And then it essentially, like a spring thing happens, and it flips. The magnetic field of the sun flips. And so when it's super twisted up, that's when we have solar maximum. So there's a lot of events happening. There's a lot of sunspots. And then it flips, and it sort of calms down for a little bit, and that's solar minimum. And so we're essentially right now in a solar minimum state. I could go on and on, but let's move on. Okay, so I'm going to try to bring it back down to Earth a little bit here. This is another super cool movie from NASA where you will see particles. These are electrons. This is the plasma from the sun. It's going to come and hit Earth. And what I love so much about this is that I studied kinetic plasma physics. And kinetic plasma physics is, what are all of the particles doing statistically? So this was super cool, because most of the people that I work with worked on magnetohydrodynamics. And that's what is the fluid behavior of this plasma. And I'm looking at what happens with the individual particles, because you can approximate something with a fluid, but it's not really a fluid. All right, anyway, I digress. Okay, here we go. So here's the Earth. Okay, all right. Here's our Earth. We've got this big coronal mass ejection with billions of tons of particles heading towards it. And you can see the particles are deflected because of Earth's magnetic field. But this is a really intense radiation storm. And so we're just getting pummeled. It sort of gives you this beautiful perspective of just exactly what Earth's magnetic field does for us. And here you can see these are our magnetic field lines, okay? And we'll watch particles propagate down here again. And do we see the aurora on this one? No, we don't. There's another one that shows the aurora. But I love this picture, because we are out here in this amazing space and this tiny little thing, and protected by this incredible force field. It's just magnificent. All right. So now we're back on Earth, and we're in Vermont. So I talked a little bit about this already. We are at a very high latitude, so we are more susceptible to geomagnetically induced currents. These are these strong currents I was talking about. And so our people here, like VEC and Velco, are monitoring this. Velco, let's see, when I gave this information 4 years ago, I think it was, I haven't spoken to these guys in a while, they had 9 monitors around the state just to look at geomagnetically induced disturbances. So this was really, really cool. And then they share their information, and the local power grids are looking at this too. And one of the things that I absolutely love about Vermont is that the folks here are so interested in trying new stuff. There are places in the country that would love to have these disturbance monitors on their power grids, but they just don't quite have access to it yet. And Vermont has them already. It's really special. It's really, really special. Okay.
Out of curiosity, Sarah.
Yes, Sarah.
Vermont, as part of their, their efficiency that we all get charged on our electric bills, would that help pay in part for those monitors?
That's a really good question that I don't actually know the answer to.
I know that Vermont made themselves significantly more efficient with that little bit extra we all pay on our electric bills.
Interesting. That's very, very interesting. I haven't spoken to these guys in a while. We talked for a little bit about putting more monitors here. But at that time I was at NASA and we were trying to find funding to do this. Yeah. And one of the great things about my job currently is I get to run competitions, and we just made an award to an absolutely fantastic scientist who is going to put more monitors across the US. Yeah, it's very cool. What they really want to do is put tons of these, they're called magnetometers because they measure magnetic field. So they want to put like an entire grid of these things across, I mean, ideally we'd have them across the entire planet, but National Science Foundation is only going to fund them basically to go across the United States. So people want to do that, and we're working on it, and it's really cool, and it fits right into our national actions on space weather. So this is an effort that has been going on for a long time.
It's interesting that FEMA is part of that.
Yes, and there's a reason for this. I think there's something like 15 or 20 agencies that are part of this National Space Weather Action Strategy and Action Plan. So this was originally put out in 2015, and then with the Trump administration, it was revised. This is type of thing happens. So for decades, people have been putting out plans and then revising them. So this time around, folks got together from all of the major agencies and said, okay, space weather is such a big issue. If something really catastrophic happens, and say along the East Coast, we lose, like this is, you know, Armageddon scenario, and we lose power, how does the government still function? What are the priorities for the nation? What comes first? How do we deal with it? How do we put resources into developing the science so that people can predict these things? How are agencies like FEMA going to use this information? How is NOAA going to use this information? So it's really cool. I got to work on this in my first couple of years at National Science Foundation. I got to work on this. And this, for me personally, was amazing, right? So the idea basically is that NASA monitors space weather with the satellites. NOAA does some modeling, some monitoring of it too, but NASA's assets are the ones that are most important at the moment. The information is fed to the scientists who use it in their models. Scientists at NOAA use this information and they put out alerts. Say, we think a storm's coming, this is the probability of it. And then the information is communicated also to things like the power grid operators and to Department of State, Department of Defense is interested in this. Department of Defense wants to know if something's happening to the communication satellites, is it happening because it's a natural phenomena or is it happening because of an enemy of the state, right? They also want to be able to protect their assets. So this was all happening under the auspices of the White House. So I gotta just, like, one of the things I love about my job so much is that I get to do things like go to the White House grounds. Like, so cool. The first time I was there for a meeting, I was like, oh my God, I'm from Wolcott, Vermont, and here I am doing the nation's work, and I can see the White House. Anyway, you guys can do that too. You can do that too, all right? I had a lot of luck, and I had a lot of help, and I'm here to help every single one of you. So if you all reach out to me, I will do everything I can to help you on your career path, all right? I am deadly serious about this. I tell this to every audience that I speak to. Contact me, please. I'll put up my information later. All right, so my actual job. How does the National Science Foundation fit into this? We support the basic research, that it underlies all of the modeling, all of the ability to predict, all of that between the National Science Foundation and NASA. Department of Defense puts money into it too, but it's not quite as open. The National Science Foundation accepts proposals from any scientist at any time. We have specific areas that we focus on, but it's sort of the hippie of the agencies. We want to see what the scientists think is really cool and really important. NASA does really, really cool stuff, and I owe my career in a lot of ways to NASA. They are what we call a mission-driven agency. They say, this is what the priority is, scientists go do it. NSF says, scientists, we want your idea. Give it to us. And then we send it out to review, and then we make decisions. All right, so these are the facilities that happen to fall in my program. So I have 1, 2, 3, 4. These two, one's in Alaska and one is in Canada. There's Arecibo, that's down in Puerto Rico. We've got this one in Massachusetts. And this one is really, really cool. This is called the Jicamarca Radio Observatory. It was built at about the same time that Arecibo was built, and it's in Peru. It's outside of Peru. And it is, you can sort of tell from this image, it's just like fields and fields of these little antennas that work together as one massive radar. Yes, Sarah?
I watched a program on Sarah. I watched a program on the dark matter and black holes, and I'm wondering, is that the same place in Peru that they were looking at black?
No, that's a really good question. That's further up in the mountains, and it has different power structure and measures different wavelengths. So this measures the upper atmosphere, and then they are looking way out beyond the atmosphere. So the beam that comes out of this thing is not strong enough to get all the way out there.
Thank you.
You are very welcome. Yes, Caitlin.
I was wondering about how many applications you get and how many you actually grant.
Good question. What is our success rate? The scientists are always asking us this. They want to know what their chances are. Technically, I can't tell you. However, what I can tell you is that right now competition is really stiff. We have a lot of people that are doing really good science that want a lot of money to do it, and we can only afford a small fraction of it. That's about as much as I can tell you.
Project to kill me?
No, the lawyers would come after me. We've had arguments.
Your money from the government?
Where do we get our money? This is an excellent question. Yes, we get it from Congress. So the White House says for all of the agencies, we want this much money from Congress for each one of these agencies for this purpose. And Congress looks at it and says, nah, I don't think so. We're going to give you this instead. And there's a little back and forth. And then eventually we get our money. So we are a federal agency, and we are subject to things like government shutdowns. So I don't know if you guys are all super well aware of that, but that was not a ton of fun. Okay, way in the back.
I'm just wondering how places like this affect the local populations and the environment.
That is a fantastic question. How do places like this affect the local environment and the local population? This is an issue that I'm working on because two of these facilities, Arecibo and Jicamarca, are 60 years old. And so they've had an impact on the environment. And things like the A-misers here, which are in Canada and Alaska, have been up for 20 years. They've been up for 20 years and in the planning for much longer than that. The idea is that there's not a lot of impact. The reality is there's impact. So NSF right now is working on closing down the first facility it's ever closed. And it happened to be one that was in my program. And it was in Greenland. So it was a radar that was owned by the Air Force, somebody like that. It was moved from Alaska to Greenland 30-something years ago and sat on an Air Force base that closed down. And then NSF is still doing science there. And then eventually we went, the science return is not worth the money anymore, so we need to close this thing down. How do we manage the cleanup? And that is a whole big thing between us and the Greenland government. What is right? What's our liability? What's not the responsibility of the National Science Foundation because it belonged to a DoD, it was a DoD installation for a while ago. So one of the things that is super cool about working on facilities right now in this day and age is that the operators are much more environmentally conscious and concerned than they used to be. So I spend a lot of time talking to the operators about diesel gets spilled. These things are run on generators. They're run on massive generators. And so you got to put diesel into them. And when you pour gas into your tank, you spill a little bit here or there. How do we clean that up? We need to make sure we clean that up. This is my personal feeling, okay? As stewards of this planet, the National Science Foundation may not necessarily agree with this, but this is my personal philosophy. As stewards of this planet, it is our responsibility to make sure that these things are not destroying the environments around them, okay? There are laws that we have to comply with, but we're still working it all out. So how's that for a bureaucratic answer? I didn't really answer your question, but it is near and dear to my heart, and I'm glad you brought it up. All right. How are we doing on time? 5 minutes or so?
No, we got to 5:15.
Oh, 5:15. Oh, I have plenty of time. Oh, good. Okay. All right, so this was, again, just to show you I should have probably put this slide earlier. This is just to show you what the radars that I fund measure. So they're called incoherent scatter radar. Just, you've heard the term now. Never mind what it actually is. They measure from about 200 kilometers. And the one in the one in Peru, they say can measure all the way out to about 10,000 kilometers. So that's out into the magnetosphere. Other scientists are a little skeptical. They're not sure it can really reach out that far. But we know that it can go out to at least a few thousand kilometers. So just for reference, troposphere, here where this orange line is, that's where we live. That's the only environment in which we can really survive. And then the auroras are happening up here. You can shoot rockets up into the auroras. This is so cool. Scientists go up to Alaska and Greenland, and they shoot rockets up. You go up in the middle of winter where it's dark like all the time, and you sit around and you wait for a storm to happen, and then you shoot a rocket up and try to measure the particles. They love it. They love it. And that's great. I'm glad they love it because we get interesting stuff out of it. Okay, and then our satellites sit all the way up here. And then there are so many cool phenomena. There's something called air glow. There's noctilucent clouds. You should Google noctilucent clouds and look for the movies. They're just amazing. They're like clouds that...
Spelling.
They what?
Spelling.
They're what?
Spelling noctilucent.
Yes. Oh, noctilucent. Noctilucent. Noctilucent? Yeah, it's pretty phonetic. But if I can give it to you later. Anyway, check out the movies. They're really, really cool. Okay, let's see. And what else did I want to show you? Oh, this is our ionosphere. So our ionosphere exists about here, sort of in this region. Okay, that's a little off topic. I talked a little bit about this already, but I'm going to go through it very formally so that you have an understanding. Most of the nation's scientists are funded in this fashion. You can be a career scientist, a civil servant, a federal employee at a place like NASA or at a place like NOAA, and more or less your funding is guaranteed because your salary comes from the agency. Not all agencies work this way, but NASA and NOAA do. And so you do the work of the agency. You do the science that the agency needs you to do. Or you can be a scientist at a small company or at a university. And most of our scientists are at universities. And so they're things like professors or soft money scientists. So these are people whose salaries come entirely from grants. So they spend a lot of time writing proposals and being rejected and writing another proposal so that they can get enough funding to support themselves. And the amazing thing about the scientific spirit is that these people love what they do so much that they are willing to do that. It is incredibly stressful. It is incredibly stressful, and people do it. They spend a lot of time being disappointed and a lot of time being angry, and I get a lot of phone calls, why didn't you fund me? Okay? So what happens is that National Science Foundation, NASA, NOAA, the Air Force, and the Navy are the ones that primarily support the research of space weather. So they put out solicitations. You can go to the National Science Foundation website and look for any program announcement or solicitation, or they call it AOs. NASA calls them announcements of opportunities. And that says, we welcome your proposals on this thing, and these are the requirements, and submit it to us at this time. They're very intensely bureaucratic documents, and it takes some help interpreting. So you should feel free to try to reach out to your program officer. If you read a solicitation, don't really understand what the motivation is behind it. So NSF puts out solicitations for various types of grants. So our core programs are basically, you can submit a proposal, say, to solar terrestrial research at any time during the year on any type of solar physics. But then we also have specific targeted competitions. So these are things like, I just ran a competition for distributed arrays of small instruments. So I wanted to see, the agency, through all sorts of priorities, wanted to see what are the proposals to put out arrays of instruments across the continent, basically, to study anything from the upper atmosphere to the sun. And then we have grants for things like operating our facilities. You have to write a proposal, which has to be reviewed and then awarded. And then we have very specialized programs for students and early career scientists. So we want to get the money particularly to early career scientists. So NSF has review criteria. One is, how good is your science? Two is, what is the impact of your science on society? So we want to know, you got this great idea and that's fantastic that it's scientifically relevant, but we want to see, how is this actually going to improve the life of people across the nation? And one of the ways you can fulfill that criteria, one very important way, is to increase diversity on your teams. So as we know, science has largely been dominated by white men for a very, very long time. And we have gotten amazing places from them. But in this day and age, we need all minds from all perspectives, from all backgrounds, on deck working on these problems, because it is the diversity of backgrounds, the diversity of experience that leads to diversity of ideas. And so NSF pushes this, and we have our wonderful colleagues at other agencies that roll their eyes at us and say, oh my God, you guys, we just want to get this thing done. And NSF says, wait a minute, it is super important that everybody has an opportunity here. Okay? So that's incredibly important for NSF. And it's led to some good stuff that wouldn't have come about otherwise. All right. I do mean lovingly. They give us a hard time lovingly, because every time they try to work with us, we say, you got to do something about broadening participation. We want to see, if you're going to work with us, if another agency wants to work with us, it's great that the science is really important and that it's a national priority. But we want to see what other ways it's going to impact society, and we want to see how you are bringing in the next generation in a very diverse way. All right. So one of the things that we support are institutions to host research experiences for undergraduates. And I would highly recommend that anybody who's interested try to apply to these. So these are ones that are for Geospace. So Geospace is basically the study of the ionosphere and the study of the impact of the sun on Earth. So you can go down to the Harvard-Smithsonian Center for Astrophysics, which is on the Harvard campus, and do research there. The University of Colorado, Boulder, these are all amazing institutions. Colorado has had a long-standing, very, very strong program. So has University of Michigan and Alabama Huntsville. Puerto Rico is a really, really interesting opportunity. If you want to go down to work at Arecibo, or hey, you just want to go to Puerto Rico and check it out and do some science, go check out the research experience for undergraduates there. So these institutions write proposals to NSF. NSF evaluates them, awards them, and then they hold competition. So you guys would like apply to some of these things. And they provide things like stipends. Let's see. I don't have the information here because I think the salary for these things is dependent on the institution. But they'll pay your salary, and I think some of them also provide you a place to live, but you may have to cover some of it out of the stipend. It depends on the situation. If you're interested in this, contact me. I can help put you in touch with the folks that have active REUs, and you can apply for them. I would highly, highly recommend doing this. I did not do this as an undergraduate, and it's something that later on I wished I had. When I was at UVM and in college, one of my best friends at the time went down and did an REU at Arecibo. It was really cool to hear about it later on. Okay. This is another thing that I think you guys should consider. If you think you want to go into science, maybe you want to go to grad school. It's a long ways off, but it's never too soon to dream. You can apply for something called a Graduate Research Fellowship, and we actually encourage students to apply to this a year before you leave undergrad. So your senior year of high school, oh good God, your senior year of undergrad, you should be applying for these things. These things are based on you. They are based on your story. They are based on your potential. You do have to propose a science project, but they are not judged so critically on the quality of that science project. They are more focused on what is your potential. Where are you coming from? What is your enthusiasm? What do you want to do? So I would really, really recommend checking these things out. They support, it's for 3 years. You get $34,000 a year and $12,000 of educational allowances that go to the institution. So the thing that's really unique about this is that it sets up a good dynamic for you as an independent person, as an independent researcher, as somebody who is in control of your career. Typically, when you go to grad school, you're sort of at the whim, of a professor that you've decided to work with. And generally, like this is what happened to me. I had a pretty average experience. I went to somebody, he said, I have a job, you look interesting. I said, okay, I'll do whatever you want. And he said, all right, here's a project for you. All right. That happens a lot. Sometimes they work with you and you try to figure out a project if you have something that you're interested in. This guarantees your salary. You get to choose the project you want, and you get to choose your advisor. So it gives you a little bit of leverage. If something's going on, this professor's not working out for you, this project isn't working out for you, no big deal. You can switch, the money goes with you. Okay? I think you can even switch institutions too because this goes to you. So it's really, really important. I can't stress this enough. People get into this mindset, students get into this mindset that I've started this project, I've started down this path with this team, and I have to continue. And let me tell you, if you're miserable, it's not worth it. I mean, grad school is hard. Being a scientist is hard. Anything you're passionate about is hard. But if something is legitimately not working for you, change it. go do something else. Life is too short and you have too many opportunities. So this thing provides you a mechanism to do that easily and stay in control. Okay. Oh yeah, it can go to, it's portable, goes to any institution. There it is right there.
May I add something to that?
Yes,
Liz
please.
Solsey. Just to let students know here that this is feasible. Within the last 3 years, 2 of our graduates have received these awards. One is at the Woods Hole Oceanographic Institute, and the other is at the University of California, we said. So it's definitely feasible.
Excellent, excellent. Did everybody hear that? All right, there have been 2 students, you said, from here. 3?
Past 3 years.
Past 3 years. Oh, 2 students in the past 3 years. That's amazing. It is amazing. So one of the things that Vermont has going for it is that it is, believe it or not, one of the things that has going for it is that it's not a state that has a big research infrastructure. Okay, so there's like California, Colorado, Michigan, Maryland. Those states have big research infrastructure with high-powered R1 schools that do top-tier research, and that's really fantastic. But the National Science Foundation and other agencies have things called the EPSCoR program, which is focused pots of money dedicated to states like this that do not have highly developed research infrastructures. So when you say you're from an EPSCoR state and you apply to something like this, it automatically garners you a little bit more attention. Okay. Okay, the other thing that I want to point out, this is maybe a little far down the road, but I want you to be aware of this anyway. NSF has postdoctoral research fellowships. So my postdoc was covered by 2 fellowships, one from NASA, and then I won this one. And one of the ways I won this one, well, I had a good science idea, but I made the pitch that I was originally from an EPSCoR state, and that what I wanted to do with this money was help develop research here. Okay? It's one of the reasons I'm back here now. We give you a stipend of $65,000 a year. Now, that's pretty good. It's pretty good. There are other agencies that will pay you more. There are other institutions that will pay you more, but this is money that's all yours. You get almost $30,000 a year for benefits and travel and whatever equipment you need. When I was on this fellowship, I traveled so much. And it allowed me to go sit at the University of New Hampshire and hang out there for a month while I worked out a problem with somebody. And if I hadn't had this, I wouldn't have been able to sit there for a month. I would have had to make travel plans that would have had to been authorized, and maybe I could go for a week and a half, and then I'd have to come back, and then I'd have to go again. So this provides really, really unique opportunities. One of the one of the restrictions is on eligibility is that you must be a citizen or a green card holder. So this cuts out it cuts out all of the international students, cuts out anybody who comes from another country and wants to do research. This is only for US people. And then there's a bunch of other things. There's no deadline, you can submit anytime. Yes, sir.
Is that Ph.D. for less than 2 years?
Yeah. So the idea was that we are really trying to target this at people that are fresh out. So because one of the things that can happen is that you can be in this postdoctoral research cycle for a while. So a postdoc is typically 2 years. In our field, it's not uncommon for people to do a 2 or maybe 3 of them. So what we're trying to do is just get the people that are out of their PhDs and not the folks that have been around for a while, because in principle, they should be transitioning towards different types of jobs, either full-on soft money or they should be looking for permanent jobs. Okay, and then we tried to do things like allow some flexibility for you had to take time off to care for family or something like that. It's what we tried to do. Okay, so these are some of the opportunities that are available for students and for early career scientists. NSF is just one agency that has this type of stuff. NASA has a ton of this kind of stuff too. All right, So I do want to talk to you a little bit about how funding decisions are made, because I started this job. I was so excited to start this job because I wanted to know how on earth decisions were being made. Like, it's super cool to do the science and everything, but how the heck did people decide what's going to happen? So NSF and NASA, for that matter, really rely on the community of scientists to review the proposals. So I literally cannot make a decision on any proposal myself. The proposals have to go out. We have to have at least 3 people look at it. They submit written reviews to us. They don't get paid for it. They do it because they want their proposal reviewed and they want the chance at winning money. Okay? So these reviews then come to me, and we like to say, they inform the program officer. And what I do is look at the reviews, I look at the money that they've asked for, I looked at have I funded this researcher in the past, how many proposals have been awarded to this particular institution, are they doing science that we've funded before or not? How much of that science are we funding? Because we need to make sure that we're funding all of the different types of science and all of the different types of institutions and all of the different people, okay? How urgent is it? You know, what is my division director going to say? I make a recommendation. I have to write an analysis that says this is the proposal, these are the reviews, this is why I'm making this recommendation. And then it goes to my division director, and she looks at it and says, yes, I agree, or no, I don't. Usually they say, yes, we agree, you've made a good case. But sometimes they come back and say, you got to make a stronger case, this one's not good enough. So I'm going to end on this slide. One of the first things that I learned in grad school was I went and I sat on a review panel. So sometimes we get all of these scientists together and they've written their reviews, and then we bring them together and they hash it out over like 3 days, and they prioritize what proposals are the ones that they really think should be awarded. And the first time I sat on one of those panels, I was like, oh my goodness, this is amazing. I have to talk to everybody in the entire community about my ideas all the time. Because those people that you're talking to at conferences, that are reading your papers, they're the ones that are going to review your proposals. And so I want to know what my worst critic thinks of my idea. I want them to tell it to my face so that when I write a proposal, I have addressed that idea. So talk to your program officer, talk to everybody that you possibly can. And I know this is super hard for introverts, so pick the people strategically that you want to talk to, okay? But talk to everybody you possibly can. When you get to the stage where you have a PhD, or you want to offer some type of service to one of the agencies, contact the agency. Right now, you are at the beginning of your careers, and it is absolutely amazing. And you are an expert in what you want to do, and you have some skill that needs to be honed. And you are going to be an expert in something. And so I tell early career scientists this all the time when I call them and I say, I need you to review. And they go, I don't know, I'm not an expert. And I tell them, you are a PhD. You are an expert, and I need your opinion. So your perspective is valued, and this is an amazing way to learn how the entire bureaucracy works. So you'll get there if you want to, if you have the opportunities. And I am here to try to help you find the opportunities that you want. All right, thank you all very much for your time and attention.